Okay, you can think of this as the continuation of this long sequence of videos about ridiculously huge numbers, but it's mostly going to stand alone. It's going to be about the Goodstein sequence. The previous one, we talked about the weak Goodstein sequence, and that's really a toy model for the real thing, the Goodstein sequence. And it's very similar, so you probably want to watch, well, of course I just said it was standalone, but actually you'd probably want to watch that video first, the previous one about the weak Goodstein sequence. But it uses what's called hereditary base n notation. The other thing is I already got a comment on one of the previous videos that I shouldn't just refer to Wikipedia as a source, but I love referring to Wikipedia as a source as long as I read it carefully and vet it and think it's carefully done. And this, the article on Goodstein's theorem, which talks about Goodstein sequences, is very well done, I think. So I'm going to actually just click over to that and lead you through that and add my own details to it, but it's actually pretty well done. If you want to pause the video and actually just look at this page, Goodstein's theorem, you'll see it'll be better if you don't read it off the video, but I'll go through it, at least the important parts. So what does hereditary base n notation mean? Well, let's just cut to the chase here. Like 35 written in base 2 is 2 to the 5th plus 2 to the 1 plus 2 to the 0. But the thing is that we make sure that the coefficients, or like here, 100 is 3 to the 4th plus 2 times 3 squared plus 1. The coefficients have to be numbers in base 3, for example. They're just 0, 1, or 2. But the exponents can be any number. But wait a minute, what if we actually take the exponents and write those in base 3? And if those involve exponents that are bigger than 3, then rewrite those. Okay, so for example, 35, 2 to the 5th plus 2 plus 1, well, 5 is 2 squared plus 1. And finally, we've only used 0s, 1s, and 2s. And notice this 2 is special. It's really a 1 times 2 plus 0. But we've used just 0s, 1s, and 2s. And then 100 is 3 to the 3 plus 1 plus 2 times 3 squared plus 1. So we don't use any number bigger than a 3. It's kind of cute, actually. It's just a fun little thing to think about. But it's neat that it has such an incredibly deep consequence in the Goodstein sequences. Okay, so Goodstein sequence, very like the weak Goodstein sequence, but we use hereditary base n notation. So, for example, G of 3 is going to be the Goodstein sequence. We start out with 3. We write it in base 2 notation, as they say. Hereditary base 2 notation. But you know what? Here, there's no hereditary about it, because the 1 is just a 1. Okay. Then we switch the base to a 3 and subtract 1. This is going to look pretty familiar. 4, the base goes up to 4. We subtract 1, and that's provoking a crisis. And so we have to rewrite that as a 3. But now that's less than the base, and so we just go 3, 2, 1, 0. That's exactly like the weak idea. G of 4 has just one little bit where we have to use the idea of hereditary notation, but it makes a huge difference. Remember, the weak Goodstein sequence for 4 did not last too long. But when we use hereditary base notation, 2 to the 2, each of those guys is the base. And so those both get promoted. So instead of just thinking of this as 2 to the 2 and that being promoted to 3 to the 2 like we did before, that gets promoted to 3 to the 3. But there's a crisis because I subtract 1, and so I just have to write that out. 2 times 3 to the 2 plus 2 times 3 plus 2. So that's already up to 26, which is bigger than it was in the weak case. Now I promote every single time I see the base anywhere, even in an exponent. But here, there's no exponents anymore. Here there was a 1 in the exponent, so I promoted it there. Here it's not too bad. I just get 2 times 4 squared plus 2 times 4 plus 1. Then that decrements. Then I get a crisis. I have to rewrite. Then it goes to 2 times 7 squared plus 7 times 4, dot, 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 dot. And this is a pattern that we actually saw, this idea of you go down, 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 and then crisis after crisis after crisis, and then it starts eating away into these digits, where these like the 6 and the 7, and then it starts eating away into the squares. So here's one place where it gets eating away into this guy. 2 times 11 squared plus 11, the base is 11 here. Then you promote him to 12, but you have to take 1 away. So you still got an 11, but it's only a regular 11. It's not the base anymore. So very similar to the previous ones. But that's about, only for those small values do you just get a small difference between the weak Goodstein sequence and the full Goodstein sequence. Already, if you look at this number, they actually calculated it out, how many steps it takes. Okay, pretty big. So here's a great example, 19. We start out with 19. That's 16 plus 2 plus 1. So that's 2 to the 2 to the 2 plus 2 plus 1. So now notice we're getting chains. We're requiring chains of exponentials. That should sound familiar. That goes back all the way to the Knuth double up arrow notation. But in fact, it's going to relate to even more powerful things with the fast-growing hierarchy. So that gets promoted to 3 to the 3 to the 3 plus 3. Already, just at the very next step after 19. Wow, that's a pretty big increase, except by the standards of these videos, of course. Now, 4 to the 4 to the 4, and the 3 was the base, so it gets promoted to be a 4, but then I subtract 1, and it's a 3. Now I promote the 4s to 5s, and I decrement, promote the 6s to 1, 7s to 7s. Ah, I've got a crisis. Already, it's getting pretty big, almost out of the reach of just sort of scientific notation. And I've got a crisis, and here's where the interesting stuff happens. 8 to the 8 to the 8 minus 1. Well, that's 8. I've got to expand it out in terms of 8 to the 8 minus 1, and 8 to the 8 to the 8 minus 2, and 8 to the 8 to the 8 minus 3, etc., etc., etc. So it's all this. Coefficients are all 7s. So it's like when I take 1,000,000 and I subtract 1, it's 999,999. I've got a bunch of 7 coefficients, and then I've got all the powers of 8 from 8 to the 8 minus 1 all the way on down to 0. Well, this is 8 to the 8 minus 1 written out in terms of base 8 notation. And this is 8 to the 8 minus 2 written out in terms of base 8 notation, etc., 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 down to some fairly small numbers in base 8 notation, and then finally just single digits, and then down to 8 to the 1, and then just 8 to the 0. Okay. And so already, this is getting pretty complicated. Then at the next stage, I don't have a crisis. I just promote every single 8 to a 9. And so notice how this is working. Yes, the ones in the base position get promoted, but also these ones up here. Every time I see an 8 here, that's the base, that's the magic number for this step, it gets promoted to a 9. And that makes this guy grow tremendously fast. Now imagine if I just had like a 2 to the 2 to the 2 to the 2. That's not the world's biggest starting number. That'd just be like 2 to the 16. That's going to do this at multiple levels now, instead of just this level and this level. Okay, so this guy looks like it's growing ridiculously fast, and yet we might have a suspicion from that weak Goodstein example that the subtracting 1 might actually keep cutting into the structure here, and actually, in fact, it's true that every Goodstein sequence eventually terminates at 0. But how long is it going to take, and how could you prove that it terminates? Okay, so if you go down a little more, it talks a little bit about the proof of Goodstein's theorem. This is where I'm going to add a little bit more, because it's not, I don't think it's incredibly obvious how this works. And I'm not going to say too many details myself, but show you what an example of what they're doing. Okay, so what we do is we track, let's go ahead and track that 19. This is the 19 we started with, written out in hereditary base 2 notation. And at every stage, at every base, I'm going to write a parallel expression using ordinal arithmetic. And what I do is every time I see the base, whatever that base is, I replace it with an omega. Remember, that's the simplest kind of infinity. And any ordinary number that's less than the base, I just replace with an ordinary number. So in fact, to make it more parallel, I'll just put a 1 there. Okay, so the 19 you write out in base 2. Well, if I have the parallel expression, it's omega to the omega to the omega plus omega to the 1 plus 1. Now this is a tremendously large, or a pretty large kind of infinity. Okay, and so you might think, what the heck use is this? Well, what's going to happen, the claim is that these guys are always going to be greater than or equal to this expression on the right, but that these guys are actually going to decrease monotonically as we go. So this one starts out growing, and we're trying to show that it's actually eventually going to go to 0. Well, if I have a sequence of things, each of which is bigger than the corresponding thing over here, but if I know these guys are always going down, that's a good thing. And then we have to know one other really important thing about ordinal numbers. They're well ordered. If you want to look up well ordering, that's a really good thing to look up. And one of the consequences of that is that any decreasing sequence of ordinals is finite. And we'll see a little bit more specifically about what's going on with that with this example. Okay. So with the 19, we saw the 2 to the 2 to the 2 plus 2 to the 1 plus 1, then went to the 3s, the 4s, the 5s. And what's happening here, I've got omega to the omega plus omega plus 1. Then I decrement that. Oh, okay, that is going down. And as these bases go up, the magic here is that the omegas stay the same. They're not changing. So they're unaffected by this base change, which with these numbers makes the expression grow so fast. But these guys are unaffected. So you might think, well, it's because these guys, this is a ridiculously huge upper bound for this quantity. This is 19, and this is a huge kind of infinity. But bear with me, it'll actually work. So one of the tricky bits is that when you get to something where you can't just simply subtract 1. This is subtracting 1 here and changing the base. This is just literally subtracting 1. But that's not what happens here to here. Remember the rule, this expression with the 3s gets turned into things with omegas for 3s. This guy has 4s, and then this 3 is just an ordinary number 3. It's a number that's less than the base, and that gets put in as a 3. So this omega, which is a kind of infinity, under this rule gets destroyed and turned into a finite number. And then that one, in parallel with these guys, just ratchets down. And so a little bit of the infinity structure of this ordinal has been destroyed when we had this crisis. So every time we have a crisis, and those happen quite regularly in this sequence, we're actually going to make a significant dent in how big this kind of infinity is. And that's really formalizing the idea we had in the weak Goodstein sequence of, yeah, these things seem to get big, but this chipping away by 1s eventually erodes the structure. This is a way to make that statement precise. Okay, so let's see. We get to 7 to 7, 7. That's omega to the omega to the omega. What happens there? Well, they've written out, I just wrote out in a slightly different way here. Remember, 8 to the 8 to the 8 minus 1, that's a number with all 7s in base 8, and the number of these things is 8 to the 8 minus 1. That's how many 7s you need. Actually, it's 8 to the 8 7s. And so it's 7 times 8 to this big number expressed in base 8, and then times 7 to this big number expressed in base 8. This is just what we had on the Wikipedia. Okay. What's the corresponding ordinal upper bound? It's just take every single time you see an 8 here, and you place it with an omega. That's a massively complicated expression, but all we need to show is that it's strictly less than the thing we started with. The claim is it's less than omega to the omega to the omega. And that's a true fact about ordinals. I don't have an omega to the omega to the omega. I don't have infinite to infinite to infinite here. I just have something that's a bunch of coefficients of powers of omega, and yes, that has powers of omega, but the iterated power, these guys up here, are finite. And no matter how big this, if you replace the 7 with a billion or trillion or any of the big numbers we've discovered so far, that's not going to be bigger as an ordinal than omega to the omega to the omega. Because that's what happens when you take the limit of all expressions of the form omega to the omega to the n. And so this guy, even though it's complicated, is less than this guy. Okay, so that keeps happening. Every time we have a crisis, maybe a simple ordinal expression, perhaps, is replaced by a more complicated but smaller one. Okay, and so the claim, I'm not going to go further in terms of showing it explicitly, is that the ordinal sequence, that sort of partnered sequence, is strictly decreasing, and therefore it eventually goes to 0. And again, if you want a proof of this important, very, very important lemma that any decreasing sequence of ordinals has to go to 0, you can look at the article on well ordering or something, but you can even see why, or sort of how that's happening. Every time I subtract, every time the crisis happens, I decrease the structure. And I'm going to keep biting into this structure, and it's going to take a long, 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 long time, but I'm going to keep biting into this structure, and the 7's going to disappear, and then that omega is going to get replaced by some finite number, whatever base it happens to be, and then omega 7 eventually is going to get replaced by a finite number. All of these guys, these omegas, are going to get replaced by finite numbers. they're going to be, and it's toward the end, they're going to be unbelievably large finite numbers, but they're finite. And then, once everything is finite, it's just going to start decrementing down, 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 down. And so that's a very good way to formalize this intuition that this incredibly large growth is still not structurally sound, and you can eat into the structure and it will die eventually. Okay, so how fast does the Goodstein sequence grow? Well, I'm going to just show you a little bit of a table here. I think I need to make that a little smaller. Okay. Here's the synopsis of, if you start with a certain value, here's the seed, and here's that seed expressed in terms of hereditary base 2 notation, which is clearly going to be important for how the sequence gets started. And then g of n, script g of n, is the actual Goodstein function, the length of the sequence. You see these -2s? Those are familiar from the previous video. And you see the fast-growing hierarchy. Ah, interesting. Now, there's another hierarchy that I could have introduced you to, which is called the Hardy hierarchy, referred to up here, these big H sub alpha. It's a significantly less fast-growing hierarchy, but it's got the same idea of recursion sort of massively applied. And if you use that hierarchy, there's a really interesting parallel here between the structure of the n in hereditary base 2 notation and which function in the hierarchy you have to use to describe how long the Goodstein thing works. So here you can see 2 to the 2 plus 1, that basically gets replaced by omega to the omega plus 1. 2 to the 2, omega to the omega. Okay. So it's that same idea of ordinal replacement, taking anything in the base and replace it by omega. Here, when you get up to 19, 2 to the 2 to the 2 gets replaced by an omega to the omega to the omega. So what that suggests is that in terms of this Hardy hierarchy, we're going to need functions that have h sub omega to the omega to the omega to the omega with arbitrarily nested towers of omegas. Okay. Now, we didn't discuss h, but it's closely related to f, and basically it's related that if you have an omega, a certain number of omegas here, you need one less omega over here in the fast-growing hierarchy. And it's not quite the same. You can see these are a little more complicated, and the parallel between these guys and this is not as tight. But the rule is basically, if you have a tower of exponentials that's n long here, the kind of function you're going to need to describe that has n minus 1 omegas in here. Okay, so now we've got this situation that should be familiar. For depending on the input, the which function of the hierarchy we need is growing. Well, that's the diagonalization idea. So we need one function that encapsulates all the fast growers for arbitrary towers of omegas. So let me go back here. So the kind of growth, getting a little bit more vague here, the kind of growth of the Goodstein function, that script g, I guess I won't use a script g, g of n, I just don't want to bother with the script notation. The kind of growth of g of n is that of a function which uses arbitrary towers of like omega to the omega to the omega, let's see if I can get in the, yeah, etc. Okay, in the subscript. Okay, but that's the diagonalization idea. So it's exactly f. Well, it's not exactly, but basically what we're getting is something that needs access to f sub epsilon naught. Because remember, epsilon naught is the limit of, well, let's just say, let's delete the n. It's the limit of this sequence, omega, omega to the omega, omega, sorry, omega to the omega to the omega, etc. Okay. So this, remember back a couple videos ago, this was an amazingly huge function. To even unpack the definition of this even a little bit just gets you incredible iterations of huge functions like f omega or f omega plus 1 or f omega to the omega. Just unpacking the function and then evaluating it, much less, creates an unbelievably huge number. And so what we're seeing, if you believe these statements, that looking at this hereditary base 2 notation gives you how much of a growth you need. That's showing that we're getting up to the level of this function f sub epsilon naught. Now, to be really precise, we aren't applying it to 19. Notice that 19 doesn't show up in here. But that's kind of like the log we saw in the last video, the log 2 base n. And it doesn't drastically change the growth rate of the function we're talking about. Okay? So roughly, we'll just put a roughly in here. Okay? And so that's why it's basically of that order. And remember the punchline. Why are we so interested in the Goodstein sequence? Okay? It's that we know, using ordinal arithmetic, that g of n, this function, is well defined because the sequence terminates. But Peano arithmetic can't prove it. Because it turns out, and this is not at all a trivial fact, it turns out that Peano arithmetic basically can't deal with functions that are of this order of growth. And that's certainly proving that, even touching the proof of that is way beyond my expertise. But that's one of the features of this story. Okay. Well, so wait a minute. If this kind of mathematics can't prove it, how are we able to prove it? Well, to use ordinal arithmetic to actually prove that all these guys really make sense, and in fact that epsilon naught kind of makes sense, and you can do like in basically induction and recursion arguments up to this level. That's something you usually get from set theory or some more powerful version that doesn't really come from ordinary induction. It's genuinely transfinite induction, and Peano arithmetic doesn't have access to that. So this funky example, for me, Goodstein has two values to it. One is that it says this function, which I think has a very natural definition, but uses ordinal arithmetic, which might be a little intimidating or kind of weird, can actually be accessed just with a slightly convoluted argument in terms of defining the sequences and all that, but something that doesn't explicitly mention ordinals at all. To define the sequence, we didn't need any of this stuff. It was just this idea of hereditary base 2 notation, or base n notation, playing this funky game and then seeing if it ever quits. And it turns out that, yes, it quits, but in an amazingly long time. So that's one reason that I find the Goodstein kind of cool, is it really gives us a natural place without infinite arithmetic where a function essentially of this growth rate occurs. Because when I first started looking at this, I thought, wow, this function, is this ever going to come up? This is just for fun, right? This is just for the 12-year-old in all of us. Well, no, it actually comes up in this Goodstein example. And then, of course, the deeper reason to care about the Goodstein is that it shows that there's this natural result that is exactly in this interesting zone of stuff you can prove using a fairly strong version of mathematics, set theory, or anything that accesses this kind of transfinite recursion induction, but can't be proved in an equally natural but less powerful version of mathematics. Pretty cool.